Right, welcome to this is CS4510. This is L17A. The topic of today is Savitch's theorem. In more general terms, Savitch's theorem is space complexity. So what does space complexity mean? What is space? Man, what an interesting question. Recall that we use this notation to denote a time complexity class, which is the set of languages which can be decided by Turing machine, which halt in time f of n steps. We wish to define a similar class known as space f of n, in which there is a class of languages decidable by Turing machines which use no more than f of n space. But what does that really mean? So first off, do you count the input towards the space? Let's say no, just to make things interesting. So you have what's here is a read-only input tab. Read-only, write move, input tape. Similar to a PDA. And then you have an auxiliary work tape, or perhaps work tapes. And this is the work tape. So you only count the space that is used on the work tape. You don't count the space that's used in the input tape. And this allows you to define, for example, a sublinear space thing. The only thing that's considered is the cells that are used on the work tape. Now, space is a very different resource than time. And in some sense, that makes it both very, very interesting, the techniques you can do in space complexity, and also the because the techniques can be interesting, but also totally inapplicable, as we'll see today. They're really, it's really like a funny thing, and it's almost not really applicable to algorithms. One of the reasons is that space complexity is not defined in terms of time and space, but just pure space. So the way to really think about space complexity is that f of n cells have already been marked off for you, and then you're only allowed to use this much of the tape on input n, right? And what that means, though, is that you can use almost as much time as you want. So you can do as much time as you want, but you must use this much space, something like this, right? The reason that's kind of problematic is it means that there are things, for example, like you can exponentially blow up time to save like a single constant amount of space, something like this. So you can do like a reverse time-space trade-off to get more, use less space at the cost of way more time. But that's, of course, totally impractical. Space complexity is also uninteresting in the sense that if you were to measure space complexity when you finish the return of an algorithm, it would always, every algorithm would be constant space, all right? Because after you finish running an algorithm, you will always get the space back, but you'll never get the time back, right? So in some sense, space is a highly reusable resource, and this makes its study almost kind of orthogonal to the study of time complexity. That said, though, we can still contrast and compare them. What is the most trivial relationship between time f of n and space f of n? Or just time and space in general?
The relationship?
Just any relationship.
Time always moves forward.
And space can stay static.
I think that's a more precise way of saying what I was saying, which is that you never get the time back. But in a more formal sense, and actually in a very physical sense, you cannot go back in time, right? There's Newton's things there. And space does not even necessarily mean memory pieces used, but maybe in a physical sense, how much of volume of something is necessary. I guess what I'm asking is, for example, let's say you have a machine that runs in a certain time. Is there necessarily a relationship about the amount of space it must use?
No.
Well, if you have, even in a physical sense, if there's a time bound, there's also a space bound, right? So if you know you only can move in, I don't know, 1 second, then there's a region that you can only explore as well, right? Similarly, if you know you halt within f of n steps, at each step you use at most one new cell of the tape, maybe less. So there is in fact a space bound. Every time there's a time bound, there is in fact a space bound. So let L be a language which is decided by a machine that takes f of n steps. Then that same machine uses no more than f of n cells of the tape. Therefore that language is decidable by space f of n. So we know that time of f of n is a subset of space f of n. Okay? So every time-bounded machine actually also has a space bound. Now, again, it's not, there could be languages in here, for example, that take like super exponential time, but only use like 3 cells of the tape. Something like that is totally possible. But either way, we know if you have a time bound, you also have a space bound, necessarily. Okay. Can you improve this? Do you think you could make this smaller? This is a very open-ended, difficult question.
Like you were saying, there's a max amount of space you can use with this amount of time. I don't know how you would make it more clear, but
Yeah. So it's kind of difficult to imagine that this could possibly be improved, yet it has. 1975, they were able to improve this to, you're not going to believe this, f of n over log f of n. Okay. They shaved off a log. The way they do that space compression kind of thing is they simulate a time f of n machine, and this is Hopcroft, Paul Valiant, something like this, HPV 1975. They shave off the log by taking the time f of n machine and simulating it on a space f of n over log f of n machine. But unfortunately, the simulation blows up the time. So the time is increased exponentially. Whatever, they were able to reduce the space it used by a little bit. Kind of weird and totally inapplicable, but you can actually simulate a time f of n machine with less space than that. It does this very complex thing where you have blocks, and the Turing machine is like block respecting and doesn't touch it, okay? And this result stood for like, HPV 75, I think. This result stood for like 50 years until like, I don't know, March or something. And there's a new improvement to this, which is the square root of f of n log f of n. So people were very surprised that you could improve this, this simulation. And the paper was called Simulating Time with Square Root Space. And basically you break the tape up into these blocks, and then there's a lot of complicated stuff there. And I just want to mention that space complexity is still kind of an active area of research in low space complexity, because we really don't know how any of this stuff works. But you can simulate the time f of n machine. This simulator simulates this machine, which takes f of n steps. It takes way more than f of n steps, like super exponential steps. But it can do so only using this much tape cells. And it's very interesting how modern this construction is. And the first part of this is just kind of like a little rant and speech, right? It comes from this area known as catalytic computing, right? Which is, imagine you allow yourselves to use some space, but you don't want to count it. So like, suppose you have RAM, okay? You also have a hard drive full of photos and things like this. So what if you could use the hard drive like a RAM disk, but keep the files on there? So the idea is take a Turing machine, instantiate it with an extra tape, the catalytic tape, that has a random sequence on it. You are allowed to use as much space there as you want and not count it, on the condition, when you halt, it's exactly as it was when you began. So given that you don't have to count this tape, you don't get to count space used on the catalytic tape on the condition that whatever you did there was reversible. So the motivation is like if you had a hard drive full of good information you don't want to delete, you could somehow only do reversible computation on this funny tape, something like this, right? This is an oversimplification, but this is like some of the new stuff that's coming out, right? And this result only came, this improvement to an ancient result only came because of this modern stuff, right? Something like this. So every space machine, every time machine has a space bound. But does every space-bounded machine also have a time bound? It turns out that's kind of surprising, yes. Another thing that's important is when we measure space is that it's important that the machine halt on all inputs, right? So, for example, we wouldn't consider a machine that's stuck in an infinite loop but only uses 2 cells of the tape. Let's say it reads and writes over and over. We would not consider that machine to have a space bound, even though it does technically use only 2 cells, and 2 is a finite number, right? We don't want to think about that. We want it to be like, it halts on all inputs and only touches this many cells. Every space-bound machine does have a time bound, so we're going to prove the following. Time of f of n is contained in space of f of n. But you could probably believe that space f of n can be generalized non-deterministically to n space f of n, which can be contained in time something, which we'll talk about later, okay? We'll prove these four containments. Time f of n is in space f of n. Why? We just kind of mentioned why. Time-bounded machine, space-bounded, okay, fine. Space f of n, why is space f of n in n space f of n? Pop quiz. N space f of n, I didn't even define it, but if I were to, what would you guess it is? Yeah.
I'm assuming you have n amount of space.
Oh, nope. N is what?
Non-deterministic.
Yes, it's non-deterministic. Okay, sorry. So you have a non-deterministic, this is deterministic Turing machines that use f of n space, non-deterministic Turing machines that on all branches, the max used is f of n, the maximum of all branches.
The total of all branches together, or the max of each individual?
If the max of each branch, for example, if one branch uses quadratic space and another branch uses linear space, then that machine, we would give it a quadratic space bound, something like this. This inclusion holds because of the generalization of non-determinism, right? Every deterministic Turing machine is also a non-deterministic one, okay? Now we are going to put every, show that every non-deterministic space machine, which uses f of n cells of its tape, can be simulated deterministically in time 2 to the O of f of n. Okay. Before we do that, let's just do the deterministic version. Okay. The proofs are a little different, which is why I want to do them separately. Why is it the case that space of f of n is contained in time 2 to the O of f of n? Right? Why is that true? Well, how many if you have, I claim that if there is a space bound, there is also a time bound. So what happens is this machine has marked off for it f of n cells of the tape and on input of size n, and it doesn't touch any more than that. That's the maximum it'll ever touch. So why is it the case that it must have a time bound? So consider configurations of such a space-bounded machine, okay? It goes C0, and it yields C1, and then it yields C2, and so on, right? Eventually, it yields CA, or CA some accepting configuration, right? What approximately is the size of a configuration? The configuration, again, is a string of the instantaneous description of the machine. About what size is that?
The size of the used tape.
Yeah. How big is that?
Space complexity?
Exactly, yeah. The size of CI for any configuration is at most the space complexity, which is f of O of f of n. Right? When we say when we say f of n here, this is technically a big O there, right? Just to give you a hint, right, Q0, W1 to Wn is the initial configuration, and this is approximately the input, right? And then this is some constant there, and so on, right? So it's approximately the size of the configuration. Now, how many configurations are there? This is a combinatorics-ish question. What is the configuration? Position of the tape head, the current state, and then the current tape. The current tape is at most O of f of n. There's some constant number of possible states, and then there's some constant number of symbols to be read and written from, and so on. That's a few constants, and then there's like some n choosing whatever in there. Either way, we can say the number of configurations is 2 to the O of f of n. The constants there that are kind of being hidden by this are themselves the machine-dependent features, the number of states and so on, right? That's all kind of hidden in the constant here. But do you at least believe that there's this many number of configurations? Okay. Assume, to the contrary, M is a machine, is a space-bounded machine, sorry. Let me say, I'll say an f of n space-bounded machine, which halts in more than 2 to the O of f of n time. If there are 2 to the O of f of n configurations, and it takes more than 2 to the O of f of n time, what may you infer?
it revisits configurations.
Yes. Now, that's the math part of the question. The programming part of the question, the computer science part of the question. If a Turing machine revisits configurations, what does that mean? Specifically, even a deterministic Turing machine.
It must pass an accepting state, or is it that it's in a loop?
Let's call it configuration CI, okay? Assume this is what happens here. You just said it actually.
Looping?
Yeah, it's stuck in an infinite loop. CI to CI will never go to CA. It'll go to CI to CI to CI to CI. It's deterministic. It's stuck in an infinite loop, contradicting the fact that it halts by definition. So M is stuck in a loop. Contradiction. Okay. So if it has a space bound, it also has a time bound. It has a larger time bound. And we don't necessarily know how to improve this any smaller, I think. But if it has a time bound, if it has a space bound, it has a time bound because there's only so many configurations. And if it were to exceed that bound, then it's certainly stuck in a loop and it's not the kind of machine we expect it to be. Contradiction. So this is how you would prove such a thing for the deterministic case. Now, for the non-deterministic case, let's just consider do you recall in the computability unit when we took a non-deterministic machine and we proved it to be Turing complete by simulating it on a Turing machine? Do you recall how we did that?
What were we simulating on the Turing machine?
We took a non-deterministic Turing machine and we showed that non-determinism in the respect to computability gave no power by simulating the non-deterministic machine on the deterministic one. Does anyone remember how that happened?
Parallel computing?
The Turing machine as defined is not parallel, does not have that ability. That's basically the idea, but in more simpler deterministic words, what would we say?
You would do one step for each possible configuration, or
You're almost there.
one step on one version and then move to the next version and do one step. And
I think you have the idea. The big fancy word I'm looking for is BFS.
BFS.
Yes.
Yeah.
So recall what we did is we constructed a configuration graph. Okay. The computation can be viewed as such a thing, okay? Right? The non-deterministic, if f of n is, suppose we have a non-deterministic machine which uses f of n space. That means on the longest branch, sorry, not on like the depth of the longest branch, because the depth is related to the time. But the amount of space used over all possible branches does not exceed f of n, okay? How many nodes are in such a graph?
2 to the space complexity?
Exactly. So let's suppose we simulate this deterministically. We have a non-deterministic machine. We simulated it deterministically as follows. D on input W. First is going to create the graph. And we know that, let's suppose it has n hard-coded here, okay? It's going to create the graph, and that should take size proportional to the graph, right? We want to measure the time of this deterministic simulator. This is going to take 2 to the O of f of n time, right? Now, how long does it take then to BFS on the graph? Do you remember the runtime of BFS?
V plus E?
Yeah, and the reason it's V plus E is because the adjacency list representation of the graph, if it's given as the input, is that size. So in fact, we usually say BFS is linear time. In the study of algorithms, though, we say V plus E because the graph size is V plus E. But it actually is linear time in the size of the graph. It's exactly the size of the graph. And the size of the graph here is?
Space complexity?
Almost, it's
2 to the space complexity?
exactly, yeah.
Because each node is a, okay, gotcha.
Yeah, exactly. And in fact, you can BFS as you create the graph if you wanted, right? Either way, this machine runs in this time. So we know that if L is here, this is a deterministic simulator that puts L here. It uses that most of that time, right? Questions on that proof? Again, a lot of cool part about the complexity theory is like you have a theorem, but then the construction of the theorem does not come from, it does not necessarily come from like advanced mathematics and chaining together theorems. It's just sometimes just an algorithm, and you just kind of like lazily chop stuff together, and then that's more how you would prove a theorem than anything else. Okay, one other thing I want to quickly mention before we get into Savitch's theorem is something called speed-up theorems. So one of the reasons we use big O, so algorithms, I guess were intuitively studied first, but then after the definition of Turing machine, did we really get the conception of algorithms. One of the reasons we use big O is because of things like the speed-up theorem, right? So what we've already proven this, but I'm just gonna remind us of what it is. You can prove that space of f of n can be sped up, quote unquote, or use less space than space of max of 1 comma f of n minus c for any constant c. Now, as you understand how big O works, that just makes sense, right? Because f of n minus c is just O of f of n. But the reason we use big O is because we were able to prove theorems like this, right? Let's inductively prove something simpler. Suppose we have space f of n, and we want to simulate this in only one less cell. Okay? We have one machine which uses some f of n tape cells. Let's get another machine going which uses exactly one less cell. Right? How could we imagine using one less cell for any f of n here? Well, any ideas? And I'll mention we technically did prove this before in a very different kind of notation.
This is the working tape, right?
Yes.
Using, adding symbols.
That's one way to do it. And that's in fact how we do it for time. You could, I don't know how to do minus a constant, but I knew how to do like divide by a constant, like f of n over 2 would be why that would be why we ignore multiplicative constants. I guess this is why we're ignoring additive constants.
Dominoes, where you have 2 symbols per.
That would also work. But remember that lecture that we talked about that? There was a way we did it for constant stuff. That's actually a stronger result than the one I'm actually asking here. Basically, one cell of the tape is a constant. So what you do is instead of using it in memory, you use it in a register. That's a fancy word because the Turing machine doesn't have either of those. But suppose you had a Turing machine that looks like this, state diagram-wise, okay? What you do is you just double the states. And then you just pretend you're reading and writing to there, because anytime you wanted to read or write to this cell, you just transition to another copy of the machine. You just double the Turing machine, you double all the states and everything, and you move between the 2 copies whether or not you were going to pretending you're reading a 1, writing a 0, something like this, right? It's as if you had something like C takes on, I don't know, G, and then you say if C, else, right? Something like this. When instead you could just say if G, else. Like you technically don't need to write down the code of C if you just the memory of C, if you just implicitly kept that in the control flow, right? Something like this. You can iterate this a constant number of times, but it won't ever get rid of the big O, right? What does this tell you about, characterize for me what space of O of 1 is? What is constant space?
It never uses, uses the same exact amount of space the whole time.
Exactly. It uses at most, say, 3 cells of the tape, no matter how big the input is. What is that, though? There's another name for that. What is a Turing machine without a tape?
Oh, it's not a PDA, is it?
Nope.
No, 'cause that's-
A Turing machine without a tape is simply a what?
I'm just guessing that with CFG or
Simpler. It's DFA.
DFA.
In fact, you can argue that space of O of 1 is simply the regular languages. Why? DFA is basically, every DFA can be converted into a Turing machine that uses no space. So that's one inclusion. This gives you the reverse inclusion, right? So these are in fact equal. Constant space is in fact exactly the regular languages. There's a second proof of this one that we could do directly, right? If a machine uses constant space, we can assert something about a DFA for it, right? We can in fact, there's only, if it uses constant space, we can in fact assert there's a bound to the number of configurations. We can just make the DFA for that, following the configurations, right? The configuration graph would be bounded in some sense, and then that's a constant size thing, which is, it is literally the DFA, right? Let's not get too into that though. Instead, let's talk about Savitch's theorem for today. So Savitch's theorem is, what's the point of Savitch's theorem? So Savitch's theorem, I mean, there's several points. The first is that it's funny, and it's like, if you talk to old people, if you take a poll of old people, maybe not people, but like complexity theorists, and you ask them, what's your favorite theorem in complexity theory? Half of the time they'll say Savitch's theorem. Why? So what is Savitch's theorem, first off? It's a non-deterministic space of f of n is contained in space of f squared of n. Okay? So first off, there are two immediate corollaries we can get from this. This is, oh, and by the way, there must be some conditions on f. With conditions on f, which we will talk about later after we finish the proof. But it's not for every f, it's for like most of the good f that we actually care about, like any reasonable function you could actually do. First off, what is an immediate corollary you can think of when you see this function, when you see this relationship? What's the first thing that jumps out to you? So this is actually a de-non-determinisifying event, right? We were somehow able to take a non-deterministic program, de-non-determinisify it in some way that used only a polynomial blowup. So in fact, what this immediately suggests is that NP space, which is non-deterministic polynomial space, is actually just equal to P space. So in fact, P space equals NP space. That's the first and perhaps the most important corollary of Savitch's theorem. The reason that's so significant is that we have proof up to polynomial factors, non-determinism does nothing for space complexity. Fine. But what about time complexity? So we don't know how to solve the P versus NP problem, right? Yet we know how to solve the P space versus NP space problem. One, we know how to solve it. Two, we don't think that it's solved in the opposite way that we think is true for P versus NP. We think non-determinism has a very strong effect on time complexity, but here we observe that it does not have a strong effect at all on space complexity. It's only a polynomial amount, right? The second thing you may think is, and this is true anytime you have a theorem in complexity theory, you should be seeing it and jump out of your seat and say, how can could I possibly apply this technique to P versus NP? Could I win the $1 million? Someone here has a way to simulate, to de-non-determinisify. Let me write that down. De-non-determinisify with only a polynomial overhead to the resource used. Could we apply whatever technique we're going to use to show this containment? Could we possibly do that with time instead of space? The answer should be no. Why? Someone else would have figured it out already. If they had figured it out already, we wouldn't be talking about this, right? So from that kind of inference, we can say that it probably doesn't apply to time complexity, but only to space complexity. And then from that, we can infer that whatever simulation occurs here probably will take exponential time or something, right? Sure, space used, we do it deterministically with only a small increase into space, but perhaps not a small increase into time. That's what one thing you can infer from this. Okay. Any questions on just the statement of Savitch's theorem before we get into the proof? So how does simulation occur? Like, both in the simulations we've done so far and in the simulations that exist in like VMware and stuff. You have one machine simulates another machine on a single step. Simulates another machine on a single step, right? In the sense that, for example, how did the Turing machine simulate the universal grammar and vice versa? Is that we constructed rules that in some sequence of steps simulated one step, right? So simulation has always traditionally been done one step at a time. You go step, 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 right? The deterministic machine simulates the non-deterministic one in kind of a dodgy way, but it still does it one step at a time. One of the reasons Savitch's theorem is so funny is it throws out this idea and instead chooses to do simulation in a divide and conquer strategy from the theory of algorithms. So recall, let's suppose that n on W accepts in t steps, okay? This is true if and only if there exists a sequence of configurations, C0 to some accepting configuration, CA, and this takes t steps, okay? What Savitch's theorem, the primary thing of Savitch's theorem is like, okay, if you can go from the initial configuration to an accepting configuration in t steps, that is true if and only if there exists some C configuration such that you can go from C0 to C, and then C to CA, each of these in T over 2 steps. So that is basically the whole Savitch's theorem divide and conquer, and we'll elucidate these details in a second. But we're going to find a configuration C such that we can go from C0 to C, and then C to CA. Now, why does that work? This is going to be some recursive call on something smaller. This is going to be a recursive call on something smaller. Why would we bother to look towards recursion here? Well, here's the thing. You never get the time back, but you can always get the space back. So if you have a recursive algorithm, you measure the time, pop quiz, how do you measure the time complexity of a recursive algorithm? A couple ways, but like just any way.
Master's theorem?
Exactly, the master theorem. You kind of like estimate the size of the recursion tree, and you're like, okay, there's this branching factor, and then you have like this, and then like that, and then you're like, okay, that's A, and then this is like N over B to the I, and then you're like, okay, well then I break it up into cases or whatever. That's the master theorem. But what is the equivalent master theorem for space complexity? There isn't one. Why? Because recursive calls, you don't have to run them parallel. You run them serially. So one finishes, the other, then you start the other, but the other runs in the space that the other one did. So you can reuse the space and have recursive calls significantly overlap in space complexity, right? So measuring space complexity of a recursive algorithm, we'll talk about it when we do the analysis here, but that's sort of the motivation about how we're able to reuse space a lot. The recursive calls will reuse space, so why not look towards recursion? That's kind of the idea, okay? So we want to write now an algorithm that does this for us, and that's what our next step is going to be. So let's write it in the general case and then figure it out for specifically a machine. Let yields be some program that determines if a machine can go from a configuration CI to a configuration CJ in T steps, okay? It has to go from CI to CJ in T steps. That's what we would like to hope. What is a base case of such a recursive algorithm?
CI is equal to CJ.
Yeah.
I is equal to J.
That's the first one. Let's just say if CI equals CJ, except if CI yields CJ in one step of delta of n, and t is equal to 1, except. So these are two base cases, right? You just check with the configuration thing. Now, if t exceeds 1, we want to actually do the programming, okay? So we need to, as we've said previously, find a configuration C and then call recursively on CIC and CCJ, right? How do we find such a configuration though? Sorry, go ahead.
Since we're talking about divide and conquer, would you recursively break it up into smaller pieces?
I think, so the reason I'm asking this question is because I think there's a funnier answer in the sense that a space complexity theorist would give a bad answer that an algorithms person would not enjoy. So in some sense, being bad at computer science would give you a better answer here. That may take a lot of, that may not take a lot of time. That may be very time efficient. But we're not measuring time at all. We're measuring space.
Just guess.
Well, we're not non-deterministic. That's almost right. This is a deterministic simulator of the non-deterministic machine.
Oh, so can we just permute until we
Yeah.
land on one? That's right.
Brute force search for the configuration. For C, a configuration of N on W, brute force search for such a configuration, return, and I'll just say Y here for space. Y of CI, C, T over 2, and C, CJ, Y of C, CJ, T over 2. Return false here. Okay, does that look right? Yeah. Okay, that's it. I mean, this is the determinant. Oh, we're not done. Actually, no, this is not it. This is just the recursive thing. Now we need to make one top-level recursive call, right? So we need to, here's the deterministic simulator. D on a W, we'll have N hard-coded perhaps. And then it calls, it creates C0 to be the initial configuration of Q0 to W1 to Wn. And then it creates CA to just be, let's say, some accepting state configuration, right? By the way, the accepting state of any machine is not unique. Excuse me, the accepting configuration is not unique, right? Because the tape head can end anywhere. It could like move 10 cells and then decide to end. So this is kind of problematic. We would hope there to be one accepting configuration. So what we just say is like two ways. One, without loss of generality, just suppose there's an accepting configuration. As a unique accepting configuration. How do you do that? Just like modify the machine. So like right before it accepts, just clean up all your scratch work and then accept them, right? That could make there's a unique accepting configuration, okay? Now we want to call yields on C0, CA. And for some number here that's sufficiently big enough so that we know that the computation will complete. But what number should that be?
Space complexity?
Not necessarily. T is the time technically here. So we have something to div conquer on, right? T to T over 2.
Time complexity?
Sure, but what is the time complexity? That's great, that's exactly it. It's the time complexity event. But what is the time complexity?
You said we're brute forcing it?
I'll give you a hint. Recall that we said, we know only one thing about n is that it has a space bound. Yet we require a time bound for it. What would that time bound be?
Two to the space complexity?
Exactly. Now I'm gonna say 2 to the df of n, because we can't like actually call an algorithm on a big O. So then we say here d is equal to some number so that n has less than or equal to 2 to the df of n configs. Okay? So find some constant d such that the non-deterministic machine has less than 2 to the df of n configurations, right? D here is the multiplicative constant hidden by the big O. How do we find d like that? There's a bad answer and a good answer for this one as well. D is dependent upon the machine. It's like the tape alphabet and like the number of states and things like this. So one way is like actually try to compute D using the Turing machine, the non-deterministic machine. I give up. Just brute force search for D. Try D equals 0. That doesn't work. Try D equals 1. That doesn't work. Try D equals 2. That doesn't work. Try D equals 3. That doesn't work. D equals 4 will work. You know, just repeatedly do that over and over, and eventually you will find a D that does work. And you'll still halt within a certain amount of space, right? Forget the time. The time can be whatever. But we want to argue that that process will still use a bounded number of space. If we agree that doing that simulation, doing the simulation that way will not increase the space necessarily, because D equals 0, 1, and 2 will all use less space than D equals 3. So as you will eventually find the smallest D that this computation eventually succeeds on, and that's sufficient. Okay. Now, this is it. I mean, this is the entire simulation. Any questions on this before we get to the and analyzing this space complexity? Again, it's silly. It's like the simplest divide and conquer idea you could have possibly thought of. And there's no reason for anyone to ever do this except to prove a theorem. Like, this doesn't tell you, this is not an effective way to simulate anything, right? You couldn't, this is a divide and conquer algorithm that doesn't do anything, doesn't solve anything interesting. It doesn't, like, no one at VMware is gonna look at this and be like, yeah, we have a new simulation technique, or at all, right? This is purely to prove a theorem. And that's kind of like, one of the flavor of complexity theory is that you get to work in such high level, extremal situations that it's just kind of a little funny, you know? So that's such an example. I promised you we would analyze the space complexity, so let's do that right now. Now, let's say you have a recursive algorithm. When you measure the time, you do the master theorem. And you do the master theorem because time is not reusable. However, space is reusable. So how, if you had to conjecture, how would you measure the space complexity of a recursive algorithm?
The maximum amount of space used at one time at a configuration?
I think so, yeah. So it's like, so if you imagine, again, the master theorem, let's say we have this, right? This is some branching factor, and then there's O of n over b to the I for the depth I, and so on. And you have to count the whole sum of things. You take this geometric series and stuff, and you do that because time is not reusable, but space is, right? So in fact, some recursive calls, this recursive call can be done in the same space as this recursive call, and so on. This one is going to return and leave a single bit. So it's a little difficult to get there. I make the following claim. As you perform recursion, a series of stack frames increases and decreases, right? So the max, the first part is gonna be multiplied by the max recursion depth. Okay? Then, the size of each quote-unquote step of the recursion depth would be what? It's the size of a stack frame. Okay? I claim that product is the space complexity. Plausible? Disagreements? Okay. What is the max recursion depth here?
The number of configurations.
Not quite. We don't know that we're gonna hit every configuration, because also it's a non-deterministic machine. So there may be entire branches that get skipped. Actually, that's still a better upper bound though. That upper bound's the number I'm looking for. I guess in an algorithm's perspective, the depth is usually determined by what?
The number of steps?
Maybe I'm not wording this good. The number of steps, yes, the number of steps of the algorithm.
Recursive calls you need.
Exactly, so how many recursive calls are made? The top level has some parameters, C0, CA, and T. The next level down will have what parameters? Some C, C0, CA, and then a T over 2. And then the next level down will have a T over 4, and so on. So the depth of this will be what, right? The top level will have T, this will be T over 2, this will be T over 4, and then you stop when you bottom out, right? So how many times can you do that?
Is it the log of t?
It's log t. So the recursion depth is log t. You repeatedly divide t by 2 until you can't anymore, and that will be log of t, right? For what I is t over 2 to the I equal to O of 1 is the question. And its I is log t. Okay. That's similar analysis in the master theorem gets you that, right? What is log t though? What is an upper bound on t? At the very top level of recursion, what is that?
To the space complexity.
Yeah. This is log of 2 to the d f of n, which is just O of f of n. Okay. So the recursion depth is f of n. In fact, the size of the configuration, kind of interesting. The space complexity is the max depth. Okay? Number 2, what is the stack frame size? So what is the stack frame? The stack frame is going to contain 2 configurations and then a t, right? It's going to contain 2 configurations and an integer. The size of this is approximately the size of a configuration, and then the size of t. What is the size of a configuration approximately?
It's the size of the tape.
Yeah, which is the space bound. Exactly. So this is O of f of n. The size of configuration is O of f of n. What's the size of t? Give an integer t, how many bits does it take to store t?
Log t.
It takes log t bits. It's log t here for a different reason than it's log t here, but it happens to also be log t. What is log t?
Oh, that's n.
Yeah. This is 3f of n, which is just O of f of n. So we have O of f of n, O of f of n, O of f of n of f squared of n. QED. The space bound is O of f of n. Right? Analysis, that's where the analysis comes from, that's where the square comes from, right? Questions on the analysis? Any disagreements? Okay. So another thing about Savitch's theorem is like, can you beat this? Many people don't think so. It's just too funny, it's too elegant. It doesn't seem like you should be able to. Could you get like a 1.9 log, could you get like a f of n to the 1.9 log f of n here? Could you get like a 1.4? You know, it doesn't, I don't know where such decimals would come from, but it doesn't appear that you could beat this. At least not with any divide and conquer techniques. This appears almost optimal. So it's not obvious that you could beat this. But it is an open question, and it has been for 50 years if you could. So give it a shot. That's the first thing I'll make. The first comment I'll make. Second comment is that, again, it comes from the fact that we don't care about the time complexity. We only care about the space complexity. So this simple analysis gives us the fact that we can de-non-deterministify a space-bounded computation in only a quadratic blow-up to the space used. I mentioned that there were some restrictions on what kind of functions this applies to. And let me tell you that, what those are right now. Those conditions on F are exactly as follows. One, f of n exceeds log f of n, log n, excuse me. And two, f of n is what's called space constructible. So, first off, why this log f of n thing? Because there are machines in the way of stuff, most theorems have problems when you get real tiny. For example, we mentioned that constant space was regular languages, okay? What is the difference, would you conjecture, between log of n space versus log of log space? Those are so small. If you, let's say there's 2 to the 100 atoms in the universe, something like this. This one would get to use like 6 cells of the tape on an input the size of the universe, and this one would get to use 1 cell of the tape on an input the size of the universe, something like this. So when you get real small, it's plausible that these are equal. In fact, that such a space increase that is so small is meaningless, right? And in fact, one can prove, for example, that time of little o of n log n is the d of phase. Right? Having a log factor means you're explicitly non-regular, but if you're anything less than that, you're still regular, it turns out. Something like this can be proven. It's a complicated simulation, but it's possible, right? So when you get real tiny, there's really funny things that happen. So we just kind of like ignore those. I would argue that f of n is going to be at most log of f of n, right? So what is the size of what is the smallest possible size of a configuration, right? The configuration, well, how many configurations are there? So first off, if we have the space-bounded machine like this, it has both an input tape and the work tape, right? So what is the size, what is the configuration here? It's not just the position of the tape head on the work tape, but it would also be where the current read-only input head is, right? So it would in fact be the tuple of the input tape position and the work tape configuration. Okay. How many possible positions could you be in the input tape?
And
Exactly. How many possible work tape configurations are there? First off, what is the size of a work tape configuration? It's like the space, right? So how many possible configurations are there of that?
2 to the space complexity.
Right? So there's approximately a configuration, there's approximately that many configurations, right? So if you have a set of this size, to describe an element of that set takes log the size of that set, right? So what is log of n times 2 to the o of f of n? It's going to be log of n plus o of f of n, right? There's some math I'm hiding there, but you believe that. Well, this is the minimum size of a configuration. So if f of n is much smaller than logarithmic, the configuration still takes at least logarithmic. Why? Basically, this log n comes from the encoding of the position that has to go in the input tape, so it still takes at least that much. So this Savitch theorem cannot apply to smaller functions than log of n, right? This whole thing exceeds log of n, right? So you can't beat that. Maybe a different machine could. It doesn't matter. It's like people don't look at things like this and say, oh, what if we tried a different kind of machine that could improve this? People look at these kinds of things and say, okay, let me not care about space less than log of n. They just like give up and work on something else, right? That's the first point to do. What does space constructible mean? Space constructible basically means like the function is nice in some sense. It's not like something undecidable or uncomputable. In that a function is space constructible. F is space constructible. Essentially, if it can be computed in its own space bound. So you can go from 1 to the n to f of n in f of n space. You can, on input n1s, you can write down f of n in binary using no more than f of n space, right? Basically, all functions that you care about are space constructible, like n squared, n cubed, n log log n. Everything basically is space constructible. Something that would not be space constructible would be like Kolmogorov complexity. Something weird, okay? We don't want to do those. So that's why we do space constructible. Everything you've ever done with a big O is going to be space constructible. But it's the bare minimum requirement. And we do require this in the sense that the machine has to compute, the simulator has to compute a space bound on the simulatee, right? It has to be able to compute in this step 2 to the d of f of n, right? And it's not going to be able to do this, compute this d of f of n here if it takes more than f of n space to compute f of n for some reason, right? So that's why we require space constructibility. All right, any questions on Savitch's theorem? Let's take a break.